Okay, good morning, good afternoon, good evening, whenever it is that you're watching this. So this is going to be more of a full lesson now. So we're going to be looking at forces in motion. So this is predominantly for, well, anyone really, if you do want to do it with revision. But I'm just going to share my screen so that you can see what I'm looking at. Hopefully you can see forces of motion. And then we're just going to start off straight away by looking at a force diagram. So on the screen, a block of weight W is being pulled to the right by a force P across a rough horizontal plane. Draw a force diagram to show all the forces acting on the block. So we've got this object here, a block. I could have pre-drawn this, but that would have made my life far too easy. And it is on a rough plane, so I'm going to draw a supposedly horizontal surface. And I'm just going to indicate that it's rough by these lines. You don't have to do this. And I want to draw a force diagram. So it's got a weight of W, which is going to act downwards. And it's being pulled by a force P, which would be in this direction. Now, we would also have two other forces acting upon this. So it's on a rough plane. So that means there's going to be some sort of friction force acting behind it. And then also to stop it just going down through the earth, there has to be some sort of normal reaction force which happens in the opposite direction. Now, what we would say to this is that this is one aspect of Newton's first law. And Newton's first law simply states that an object at rest will continue to remain at rest if no other forces are acting upon it. And that would be the same if an object is in constant motion. It would also remain at constant motion if no other forces are applied. We can use this to help us with finding out the resultant force of different scenarios. So here we have a particle, and I have all of these forces acting upon it, and I would like to find the resultant force. All that means is I need to find how far is it going to be traveling in the upwards direction. So I want to work out the component of the upwards direction, and also how far would it be traveling in the horizontal component. So in order to work out the resultant force in the upwards direction, well, it's going 40 up and 5 down, so therefore the resultant force north is going to be 35 newtons, just simply 40 subtract 5. The resultant force sideways, well, it's going 30 newtons that way, 30 newtons back, so that would be 0 newtons. So we would say that this scenario here would have a resultant force of 35 newtons vertically. One thing to note, if the resultant force, I'm just going to put RF, equals 0, that means the object is in equilibrium. So that means that there would be no external force acting upon it, so therefore its motion would not change. So if it's stationary, it would stay stationary, and if it's at a constant speed, it would stay at that speed. So, moving on, we can find the resultant force of 2, 3, 4 forces by just simply adding the vectors together. So I've taken some answers and some questions out of the textbook. I'm just going to work through these, and then I'll give you a bit of time to have a go at the next few questions. So the textbook, the force is 2i plus 3j, and hopefully we should be comfortable writing that as a vector 2, 3. 4i minus j, well, that would be 4 and minus 1, because we remember I is our horizontal component and j is our vertical component, minus 3i and 2j, so this would be negative 3 and 2, and a plus b, and I'm not going to say it. Okay, and that is in equilibrium, so therefore if I add all of these forces together, my resultant force, well, if it's going to be in equilibrium, that means there's going to be 0 forces acting upon it vertically and 0 horizontally. To find the values of A and B then, well, looking at it horizontally, 2 add 4 is 6, subtract 3, and then subtract, well, add A is going to equal 0. So therefore, in this scenario, looking at it horizontally, well, 2 add 4 is 6. Subtract 3 means A is going to be equal to -3. And looking at it vertically, 3 subtract 1 is 2. Add 2 is going to be 4. And add B has to be 0. So therefore, B would need to be -4. So therefore, my equation for AI plus B would be -3I subtract 4J. And that would be my values of A and B to make sure that my line is in equilibrium. Okay, the next one, the vector I is due east and the vector J is due north. So again, vertical and horizontal components. And a particle begins at rest at the origin. It is acted on it by 3 forces. 2I plus J, 3I minus 2J, and minus I plus 4J. Find the resultant force. So again, the resultant force, I'm just going to add all these together. So 2, 1. I'm going to have 3 minus 2 and minus 1, 4. Adding these together will give me 2, 5, 4, 1, -1, 3. So therefore, I would have in the form Pi plus Qj, it would be 4I plus Qj. Work out the magnitude and bearing of this resultant force. Well, if I'm going, why have I put a Q here? I only need a 3. Oh my God. Okay. Thank God I know my shortcuts. There we go. So it's going to be a 3J. Now, if I think about what's actually happening, I'm starting at the origin and it says I have moved 4 along and 3 up. This is very similar to a scalar to vector form, which is essentially what it's asking. 4 along, 3 up. In order to work out the magnitude, I'd be doing Pythagoras. So 3 squared add 4 squared square rooted, which of course is root 25. So we'd get a magnitude of 5. And then I would also need to look at finding the angle. And I've got 2 ways I could do this. A bearing is always measured from due north, which would be vertical like this. And so the bearing that I am actually after would be this angle here, because that would be the bearing that my magnitude line would take. However, to work that out nicely, I'm going to say that I can work out this angle. And because I know east is 90 degrees, I can just do 90 subtract this angle. So therefore, to work out this angle, I'm going to do the inverse tan of my opposite over adjacent, the inverse tan of 3/4. And let me just work that out. I have not prepared this earlier. So if I work out 3/4, 0.75, and do the inverse tan, that would give me 36.87 degrees. And therefore, the angle that I need, this bearing, I'm going to do 90 subtract that. 36.87 would give me 53.1, and as a bearing that would be 0.53 as a degrees. Okay, so they would be the types of questions that you could be asked on Newton's first law. The next thing that we could look at would be Newton's second law. So I'll give you a bit of time to answer these questions. If you could pause it now. Then I'd also like to check your answers. So check your answers underneath. These are just taken straight off the exam board. And again, pause it to check your answers. And now we move on to Newton's second law of motion. So his first law was basically saying that if something's at rest, it will remain at rest. His next law is to do with acceleration, motion, mass, and force. And it's simply that force equals mass times acceleration. And for me, this is quite intuitive, because you would think if a car is traveling and it suddenly doubles its speed, doubles its acceleration, you'd assume the force would double. And likewise, if a car was traveling and it was twice the weight as a bicycle, you would assume that the car would have twice the force, which obviously it does. So a car of 2,000 kilograms has a driving force of 800 newtons and a force of 200 newtons reducing its motion. Determine its acceleration. Well, I'm first of all going to just have a look at this system and see what's happening. Well, so I've got a mass of 2,000, and that's got a resultant force, and I've got 800 newtons pushing it forward and 200 pushing it back. So F equals ma. My resultant force in the direction of motion, which would be in the positive direction, would be 600 newtons. My mass I would know as 2,000 kilograms, and my acceleration is yet to be determined. So if I want to work this out, it would just be my force divided by my mass, which would be 600 over 2,000. 600 over 2,000 is 6 over 20, which is 3 over 10, which would be 0.3 meters per second squared. Okay. On the right-hand side then, a child has a mass of 50 kilograms. What is the gravitational force acting on the child? We should note that gravity in this scenario is 9.8 meters per second to the minus 2, and it would typically be negative. However, the motion that this force is acting is going to be downwards. So therefore, we're just looking at this 50 kilograms being its weight. There is no horizontal and vertical forces, and we just want to know what's the force of gravity. So the force is going to be the mass, which is 50, multiplied by the 9.8. So 50 multiplied by 9.8 would again be 490 newtons. So that would just be some basic F equals ma questions. However, what they can do is they can pull a question like this where we need to link some of the stuff that we looked at in constant motion. And remember, when we use Suvat equations, acceleration would need to be constant. So a body of mass, 5 kilograms, is pulled along a rough horizontal table by a horizontal force. So I've got some shape here. I don't know what it is. I'm going to actually draw a table nice and straight. And it's being pulled along a rough horizontal table with a force of 20 newtons. And this is 5. Against a constant friction force of magnitude 4. So it's getting pushed along at 20 newtons and 4 newtons. I'm just going to state that this is going to be my positive direction. And given that the body is initially at rest, find the acceleration of the body. So again, if it's at rest, we know that the resultant force is going to be 16 newtons. So therefore, there is a force acting upon it. So we could work out the acceleration. So using F equals ma, I know my force is what I'm trying to work out. Oh, wait, no, my force is 16 newtons, which I know from 20 subtract 4. My mass is 5a. So what do I multiply 5 by to get to 16? So 16 over 5 equals a. Therefore, a is equal to 3 1/5, or 3.2. The distance travelled by the body in the first 4 seconds, well, as soon as I see something like this and I'm looking at a distance and an acceleration, I'm going to look at my Suvat equations. So, using Suvat, time I'm not sure of. My acceleration I know is 3.2. My final velocity, I don't know. My initial velocity, I know straight away is 0. And I need to know my displacement. So the distance traveled by body in the first 4 seconds, so I could then put 4, and then I need to link S equals U, A, and T. So you want to think about your equations. Now, S equals UT plus a half AT squared is a good shout. UT plus a half AT squared. So UT is 0. A half of A is 1.6 multiplied by 4 squared, which is 16. So S would be 1.6 times 16. Oh God, what's 16 squared? 256. So it's going to be 25.6 meters. Okay, and the magnitude of the normal reaction between the body and the table. Well, the magnitude of a normal reaction would be for this force here, which I didn't draw on earlier, which I should have done. The magnitude of a normal reaction between the body and the table. So again, I want to know what this resultant force is. Well, we need to know that our mass and our acceleration. Well, our mass is just going to be the weight of the object, which is 5, and our acceleration is going to be 9.8 meters per second squared. So the magnitude of this, so I'm not worried about direction, force equals 5 times 9.8. So our force is going to be 49, and it would be in newtons. So, yep, that would be all for the first section of mechanics on forces and motion. I hope you enjoyed and learned something new.